Okay, so now we're going to answer this question that we asked the last day, right? Which is the question is, so what is the derivative of a scalar phi with respect to the contravariant vector x mu? And we're going to solve this thing. We're going to answer this question in two different ways. The first one is going to be the simplest one. And it is, the result of noticing that, the differential of phi, which is necessarily a scalar because it has no index, right? So this has to be invariant under Lorentz transformations, is, by definition of what a differential is the derivative with respect to x mu times dx mu, right? This is clear. So this is an invariant under Lorentz transformations. But since dx mu is a contravariant vector, this means that the other object, this thing here, has to be a covariant vector. And that's, the way a contraction of a contravariant with a covariant gives you an invariant, right? So that means that this object here, being a covariant vector, should actually be identified, with an object that has an index downstairs. So this is the thing that one has to remember, that the derivative of a function with respect to the contravariant components is itself a covariant vector. Okay, so that means that d mu phi is a covariant vector. So that means this is d phi dx mu. So this is, d phi c dt, right? And then the gradient. And I write it as a row because this is a covariant vector. And, changing everything that has to be changed, mutatis mutandis, right? So then, d mu phi with the index upstairs is going to be d phi with respect to dx with the index mu downstairs. And this is a contravariant vector. So that means this is d phi c dt. And here is minus the gradient of phi, right? So that's what it is. And it has to be a minus because remember that x mu with the index downstairs has 3 minus signs for each of the spatial components. So these minus signs appear here. Okay, so once we have this, then, we can give a meaning to certain contractions, right? So examples in which we're going to find something like this. And I repeat, I'm going to derive this same relation, this conclusion here in a different way later on. But right now, this has to be like this, clearly because this contraction is an invariant, right? So one example could be, for instance, what is d mu phi? Okay, this object is going to be an invariant, obviously, because it's the contraction of a contravariant with a covariant vector. And so this is the derivative with respect to x mu, the derivative with respect to x mu of phi, right? Exactly like this. So if I write it like this, that's what it is, okay? And now it can, if I make explicit, right, what this is in components, then I have, when mu is 0, this is 1 over c squared, second derivative of phi with respect to time twice. And when mu is the spatial components, one of these two, this one actually, is the one that picks a minus sign. So this is minus the Laplacian of phi, minus the Laplacian of phi. So that means that, this, for instance, this equals 0. So that would be a wave equation, right? A typical wave equation would be d mu phi equals 0, for instance, right? This thing equals 0. And this sometimes has a name. I mean, d mu. Some people write it as d squared. Some other people write it as this object. If this is the Laplacian operator, this thing is the D'Alembertian operator. You could even find 2 here sometimes, although not necessarily, right? So is a square, is a D'Alembertian, d squared, or d mu, right? Okay, so that's one example in which you find this d mu downstairs or d mu upstairs, but there are others, right? Like for instance, remember what J mu is? So that's the 4 current, the 4 vector current, which is 0 and the density, right? The current density. So if we write d mu J mu, this is the same as the derivative with respect to x mu upstairs. This mu downstairs here, mu upstairs here, J mu. And in components, the 0th component is going to be d rho dt, because the c in here and the c in here cancel out. And then there is mu upstairs, remember? So here there is no minus sign. There is no minus sign. So this is plus the divergence of J. So, and the continuity equation, so-called continuity equation, which in fact is nothing but the conservation of current, conservation of electric charge, I mean, conservation of electric charge, can then therefore be written as d mu J mu equals 0, right? So that would be the way to write the conservation of electric charge in this 4 vector notation. So these are examples. I mean, other examples is that, you could find another example is that you can find a Lagrangian, which is, d mu phi star, d mu phi. Okay, so that would be another example. Lagrangian is a scalar, so this is a Lorentz scalar because it's a contraction of a covariant with a contravariant. And if you write this thing in with a field phi which has a complex conjugate, it doesn't have to be complex conjugate. We can even make it real. That's all right. We can do it like this. And if we write this Lagrangian, this in components is going to be 1 over, oops, it's going to be 1 over c squared, right? D phi dt squared, right? And then there is a minus sign, and this is going to be d phi, right? So that's the gradient. You agree, right? This is time component is a positive sign with a c squared. If you keep the c's, I mean, soon I will tell you that I'm not going to keep the c's, but so far I'm keeping the speeds of light everywhere. And then there is, the special components. But this one here has the derivative with respect to x mu downstairs and has this minus sign that, shows up here. Okay, so those are examples that you're going to see sooner or later. And so it's important that that you keep it in mind. And now I'm going to derive in a more formal way the same thing I derived here, which is the thing that this object, this derivative with respect to x contravariant mu is actually a covariant vector. This derivation is already good enough, but it's illustrative that we also do it in a different way. So let's do it in another way. Another way to show that derivative of phi with respect to x mu upstairs, let me put the mu clearly upstairs, is actually d with the mu downstairs acting on phi. So this is a covariant vector. So let's do this thing. So if we want to know what kind of vector this is this a contravariant? Is this a covariant vector? The mathematical way to identify this thing is by seeing how this thing transforms under Lorentz transformations, right? So a contravariant vector, and the canonical one is x mu, transforms under Lorentz transformations with this matrix lambda times x prime nu, right? So that's a transformation. It doesn't matter whether I transform from x to x prime or from x from x prime to x. The important thing is that a contravariant vector transforms with this matrix, okay? If I find that this object, as a consequence of this object transforms with lambda minus 1, that means there is a covariant vector, because we saw that the covariant vector transforms with lambda minus 1 when the contravariant vector transforms with lambda. So let us see, but which way this d mu phi transforms. Okay, so who is d mu phi? Prime. That means with respect to the prime variable. So that is d phi dx prime mu. Okay, and this, as in any change of variables, is the same as d phi dx alpha dx alpha dx prime mu. Right? If I make a change of variables from x to x prime, the chain rule says that the derivative with respect to the prime variables is a derivative with respect to x times the derivative of x with respect to the prime variables. Okay, so this is d phi dx alpha, obviously summed over alpha, which I don't make explicit because I'm using this Einstein's convention, right? But now, what is dx alpha dx prime mu? If x mu equals lambda mu nu x prime nu, what should I write here? Who can tell me this?
The lambda matrix.
Yes. And the index?
Alpha upstairs and mu downstairs.
Yes, very good. Absolutely, that's exactly what it is. Okay? So that means that this guy transforms into this guy times lambda alpha mu. Okay, so the prime guy transforms as the unprime guy times lambda. So that means that in order to compare with this, I have to invert, right? So that means that d alpha phi is going to be d prime mu phi times lambda minus 1 contracted, mu alpha. So if this guy transforms like lambda and this guy transforms like lambda minus 1, this shows that d alpha is covariant, is a covariant vector. Okay, so again, we find the same, okay? So is this clear? Remember that the covariant vectors transform, okay? Once you contract, they transform with the inverse matrix that you use to transform the contravariant vectors. This we already saw last day. So let me show you where we saw this thing. Here. You see? The contravariant vectors transform with lambda, the covariant vectors transform with lambda minus 1. Okay, so this is it. This is all we need regarding special relativity. Okay, so that means that now I'm going to close the parenthesis. This closes the parenthesis of this, mini course on special relativity. So now we go back to where we were. Okay, we go back to Lagrangian dynamics for fields. Okay, any questions so far? Any question or comment?
No questions.
Okay, so now, oops. Relativistic fields. So we have to, basically redo what we did before concerning the action in the case in which it was not relativistic, now we have a relativistic theory, a relativistic field. The action, okay, is again, so the action, this is the action. The action is still the integral of the Lagrangian, but now this is going to be the integral of the Lagrangian density times dx, dy, dz, and dt in 3 dimensions, right? And so this is d for x in relativity, so you can also write this thing as d for x times the Lagrangian density. So here I'm already taking that the speed of light is 1. Because otherwise, you know, I would have to multiply everything by c. See, if I multiply this times c, I mean, it's the same to consider the action of, or c times the action. So if I multiply everything by c, here c, then c dt would be dx0. So this is a trivial change. So it's much easier if I consider the speed of light to be 1. This is nothing special. Speed of light to be 1 means that, you know, an object that goes at 150,000 kilometers per second, now I'm going to say that goes at half the speed of light. Okay, saying that the speed of light is 1 is the same as saying that, you know, instead of going at 150,000 kilometers per second, it goes at half the speed of light. So I'm going to take these units. So c is going to be 1 everywhere, except at the very end, in which I would put the c's where they belong. And not only that, but I'm also going to take that h bar is 1. Okay, so those are units. They have a name. They're called natural units. And these natural units are very, very common, very comfortable, because you don't have to remember where h bar is. You don't have to remember where c is. And it's actually what you are using when you say that you have a spin 1/2. You should say that you have a spin 1/2 times h bar, but you do say you have a spin 1/2. That's because you're taking h bar to be 1. So it's the same idea, right? Instead of, you know, talking about actions in units of, you know, energy times seconds, okay? Now you're going to say that your action is such and such in units of h bar, all right? So let's do this. So if I have a Lagrangian like this Lagrangian is going to be a function of phi of x. Now x is the 4 vector, and it could also be derivatives of phi, okay? And who knows, maybe also x, which is now is space and time altogether. Huh? So the equations of motion are the same as before, right? So just take, you know, your field phi, which now is going to depend on a certain parameter alpha, and this is the dependence it has with an arbitrary function, eta of x, sufficiently differentiable, with the boundary conditions that at x1 and x2 is 0. So this is going to go from x1 to x2 in 4-dimensional space. So x1 is a 4 vector that has a time component and 3 spatial components, and so does x2. And so these are the boundary conditions. So we repeat the same derivation. And after we do the usual manipulations, we end up where? So ds, so if you wish, ds d alpha equals 0 is going to be the integral d for x in this 4-dimensional volume that we have now of what? So it's going to be partial of L with respect to phi minus d mu partial of L with respect to phi comma mu times eta of x equals 0. And if I write this thing as a partial, then that means that I don't have any x dependence in here. Remember that this partial here becomes total differentials if there is some explicit space and time dependence. So that means that the equations of motion are going to become partial of L with respect to phi minus d mu partial of L with respect to phi comma mu equals 0. And that is the way you guys are going to see written the equation, the order Lagrange equations for a relativistic theory, for a relativistic Lagrangian. Let me put here an L. And remember that d mu is d dx mu upstairs. Okay, so essentially what happened is that, you know, this derivative here, which was first was derivative with respect to time and then derivative with respect to space, now we can put it all together as a derivative with respect to mu as a consequence of the fact that, you know, the formalism is already prepared, you know, to accommodate a relativistic field. Okay, so this is now an important equation. Okay, now, any questions or comments? No question, nor comment? No comment?
No, no comments.
All right.
No.
Good. Okay, so let us write a little, you know, a little framework in which we will see, you know, what is the status of physics nowadays. Okay. So the situation of physics nowadays. So it's an overview. So we have classical field theory. Okay, which is in principle non-relativistic. Okay, and then we have special relativity. And if we marry the two of them, if we put them together, then we have classical relativistic field theory. So that would be, for instance, the classical theory of electromagnetism. Okay, and parallel to this, we also have quantum mechanics. Okay, quantum mechanics and special relativity do not agree with each other. They don't marry well. You cannot make a relativistic quantum mechanics. If you want to marry quantum physics with relativity, you have to do it through relativistic fields. So it's only after you have classical relativistic field theory that you can marry quantum mechanics. And when you put it together, this is what is called quantum relativistic field theory. And this quantum relativistic field theory is the last truth. Let me just write it like this. Is the last truth. So this combination of frameworks, so classical field theory with a special relativity and quantum mechanics, this object here, which, you know, is the result of quantizing a classical relativistic field theory, is the last truth in the sense that it describes, so this is QFT, that's what people call this thing, QFT. So QFT describes all the fundamental interactions. all the fundamental interactions in nature. Okay, so that's the language in which we understand all the phenomena in general in physics. Okay, and there is one example, there's one particular example that I want to mention, which is the quantum theory of electromagnetism. So QED, and that is the quantum theory of electromagnetism. And electric charges. So not just the electric field or the electromagnetic field, but also with electric charges, which in the case of the electron is the best theory up to date of all theories. Is the best theory up to date of all theories. What do I mean by being the best theory up to date of all theories? What I mean is that you can compute a certain observable, a certain physical observable. You can measure this physical observable in the laboratory, and the agreement between theory and experiment is the best of all theories. And when I say all theories, I mean all theories in any science. In any science. So that means not only physics, but also chemistry or biology or whatever you want. Okay, no other theory, accomplishes the same level of agreement between the theoretical calculation of something and the experimental measurement of the same thing. And what is this thing that can be computed with such an enormous precision? So remember the object. Oh, no, I shouldn't call it object. The physical observable, right? The observable that achieves this record is, remember, the magnetic moment of the electron. The intrinsic magnetic moment of the electron is given by the electron charge divided by twice the electron mass times the speed of light. Here I'm giving you where the speed of light is sitting, times a factor and the spin of the electron. So this factor here has a name. This G has a name, and it's called the gyromagnetic factor of the electron. So this gyromagnetic factor of the electron can be computed with an extremely high precision. And you can compute this G in theory. You can measure this G experimentally. And you can take the difference. You can take the difference between theory minus experiment for this object. Actually, you do it for this object -2, and that is because this factor G starts being 2 plus corrections. So here you measure the corrections. This 2 is what comes from Dirac's equation. Dirac's equation is something that you guys will see the next semester if you do high energy physics or or if you do, you know, advanced quantum mechanics. So, and it's the equation that describes, you know, the quantum electron with a quantum electric field, electromagnetic field. So you compute this difference, the difference between theory and experiment, and this difference is of the order of 10 to minus 12. So the agreement of the theory calculation and the experimental measurement is an agreement that goes, you know, across 12 decimal places, right? So that's the best ever. There is no other example that you know accomplishes this level of agreement between theory and experiment. And to tell you the truth, okay, this was the situation as of last year, okay? But this year, there have been new measurements of G minus 2, and they start seeing a little difference at the level of this, you know, 12 decimal place. So we will see whether this is a problem of the experimental measurement, or this requires an even more precise theoretical calculation, or what is the situation here. But still, I mean, this is, you know, a little discrepancy that now it seems to be, you know, appearing, and we'll see what the situation is, okay? Now, needless to say, the experimental measurement is extremely difficult, okay? So there is only one or two places in the planet, one or two laboratories in the planet that can, you know, do this experiment at the level of precision. And the theoretical calculation is also fantastic, right? Because it takes calculations of, you know, thousands and thousands and thousands of extremely complicated integrals, okay? And this can only be done by a bunch of people that I can count probably with the fingers of one hand only, okay? So this is not something you can do, okay? Very easily. So that's one thing. So this is just, you know, to explain that quantum field theory is the frontier of the framework in physics. It's the frontier of the theoretical language. Let us look at possible examples of a relativistic theory. Actually, there's going to be one example. So it's not plural, it's singular. So one example, one simple and at the same time very important example. And this is this Lagrangian. It's going to be 1/2 of d mu phi minus 1/2 of m squared phi of x squared. So phi depends on x, of course. Okay. Now, if you're given this Lagrangian, which by the way happens to be a very famous and important Lagrangian, this is the Lagrangian. And notice that I'm already talking about the Lagrangian, even though this is the Lagrangian density. Huh? This is the Lagrangian describing the Higgs field. So the Higgs particle is the result of quantizing this Lagrangian. That's the Higgs field. And of course, I'm only writing down the kinetic part, and this m is going to be the mass of the Higgs, okay? I'm not writing down the interactions. There are also interactions. The Higgs fields, the Higgs particle interacts with other particles, and those I'm forgetting about. But the kinetic part, okay, is this one, kinetic plus mass, okay? Now, if you're given this Lagrangian, which has now become, it has become now very, very famous, how do you find the equations of motion for this Lagrangian? Well, is dl d phi minus d mu d phi comma mu equals 0, right? So let's compute this thing. Let's do this calculation. Now, who is dl d phi? Who can tell me what this is? This part is very, very easy. So dl d phi, how much is this?
m squared phi.
with a minus sign, right? If I write it like
Yeah,
this, minus m squared phi. Yes. And now, what is dl d phi comma mu? So this means dl d mu phi, right? How much is this? Who can tell me what this is?
D mu phi with the index upstairs.
D mu phi with the index upstairs. Do everybody agree with this?
Divided by 2.
Aha. So is that a factor of 2 or not? Or a factor of 1/2 or not? So the first guy who said that is d mu phi without the factor of 1/2, how can you convince your colleague?
Because the other d phi has the same contribution, so the two cancels.
Yes. Okay. So let's do this thing. Yeah. So you're right. That's the reason. But let's try to explain it a little bit, more slowly. Okay. So how do we do this calculation? So we have to take the derivative with respect to d mu phi of L. And L is given by this. So the best way not to get confused is to write L as 1/2. And then let's write d mu phi, d nu phi, g mu nu. You agree that this is the same as that?
Yes.
Yes.
Okay, now we have the factor 1/2. I can pull it out. Then I can, here I'm doing something that I should not do, which is this index mu here is contracted, whereas this index mu here is not contracted. So I should not, call two different indices with the same letter. This is back practice. This I should not do. So that means that I have to change this letter here and call it something else, like for instance alpha. It's still the same because summing over alpha is the same as summing over mu. But this way, I make explicit that this alpha has nothing to do with this mu to begin with. It's a different index. So now I pull out the 1/2. And now I have to take the derivative of the first. So the g, I can also pull it out because it's a constant. So that is g alpha nu. And now I take the derivative of the first guy. So that's the derivative with respect to d mu phi of d alpha phi times d nu phi. Sorry, these phi's are all the same type of phi's. So let me just call it phi, 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 and phi. So this is phi, this is phi, this is phi, this is phi. So that's the first term. And now we have the second term, d alpha phi, derivative of the derivative of d nu phi with respect to d mu phi. You agree? I'm writing everything in full detail. Huh? Okay? Okay, yes or no?
Okay.
Yes.
All right, so this is therefore 1/2 of g alpha nu. And now, what is the derivative of d alpha phi with respect to d mu phi? Well, it's going to be 1 if alpha equals mu and 0 otherwise, right? So that is the same as delta alpha mu times d nu phi. And this second term is d alpha phi. And here exactly the same thing. This is going to be 0 if nu is not equal to mu, and it's going to be 1 if nu equals to mu. So that is delta mu nu. And now I have to multiply this thing by g. Okay, so the first term gives me 1/2 of mu alpha. Alpha nu is the same as mu nu with delta mu, so that is d mu phi, right? All the contraction, alpha becomes mu because of the delta, and then j mu nu times d nu becomes d mu. You agree?
Yes.
All right, and now the second one. The second one is this delta, transforms this nu into a mu, and then I have g alpha mu d alpha phi, so that is 1/2, this 1/2, d mu phi. So all in all, d mu phi, as your classmate was saying. So yes, so out of terms like this, when you take the derivative with respect to one of them, you get, an extra factor of 2 that cancels this factor of 2. All right, so then what do we find? So we find that dl d phi equals was minus m squared phi, and dl d phi comma mu, that was d mu phi, d mu phi. So now let's write dl d phi minus d mu dl d phi comma mu equals 0. So this is minus m squared phi minus d mu times that thing, so that is d mu phi. So this equation is the same as d mu phi plus m squared phi equals 0, which I can write as d squared phi plus m squared phi equals 0, or I can write as D'Alembertian phi plus m squared phi equals 0. So all these equations are, different ways of writing the same. And this equation is famous. I repeat, it describes is the equation of motion for a free Higgs field, but it was discovered many years ago by Klein and Gordon. So this is the Klein-Gordon equation. And it's one of the famous relativistic field equations that you find. It's the Klein-Gordon equation, okay? Now, explicitly, if we write this thing in components, so remember what this D'Alembertian is d mu, so that is 1 over c squared, second derivative of phi respect to time twice, minus the Laplacian, plus, and now I'm going to put all the c's and all the h bars, times phi equals 0. Okay, times phi equals 0. So that's the Klein-Gordon equation written out completely in all the components. Okay, and if we choose for phi a plane wave, so that is I over h bar et minus p x, what we find is that this operator, and this is something you can easily check, this operator plus m squared c squared divided by h squared, acting on e to the I over h bar et minus px equals 0, leads to, who can guess what this is going to be? Who can guess? I mean, when you take derivatives, you're going to bring down the exponent here. And so this is going to be some condition on the exponent equals 0. So who can guess what the condition is going to be? So you understand what I'm asking? What I'm asking is this time derivative here is going to bring down e, this e. This Laplacian here is going to bring down p's. And this m is going to do nothing. It's going to multiply. So this equation, this operator, differential operator, acting on this exponential, is going to become a relationship between E and P and M. Who can tell me what this relationship is going to be? Take a guess.
E squared equals to P squared, C squared.
Yes.
And then the mass squared times C to the 4th.
Absolutely. Yes. Yes. So this thing equals 0 leads to this condition. So this is why this is a relativistic equation, because it describes plane waves, which will become, once quantized, these plane waves will become particles. Describes, particles, relativistic particles with a mass, rest mass m. Okay, so that's what this equation does. And it starts from the Lagrangian that we wrote, this Lagrangian. Okay, so that's one example. And another example is electromagnetism. So the Lagrangian of electromagnetism is -1/4 of F mu nu minus, if there is an external current, mu J mu A mu, where J mu is C rho times J, and A mu is phi times A, and this F mu nu is, this is called the field strength tensor, and is the following combination of the Coulomb potential and the vector potential. Is d mu A nu minus d nu A mu. And the one of the examples on one of the exercises that you will do is that the Euler Lagrange equations of motion for this Lagrangian are Maxwell's equations. Not completely obvious, but it's true. To just apply the Euler Lagrange equations of motion as we have done it in the previous case, but now for this field A mu, and you will find Maxwell's equations for the field A mu, for the 4 vector. Okay, so this is an exercise that you guys will do one of these days. Okay, now, any questions or comments?
Yes. Could you go back to slides, please?
Yeah. 1 and 2.
One more.
3.
Okay. Here you said that QFT describes all fundamental interactions.
Yes.
Even gravity.
Yes. Except that, the quantizing part, so when we try to quantize gravity, it is not fully consistent. So we still do not know how to do that.
Okay.
But there is no doubt that there has to be something like this. Yeah, we still do not know how to do it. So that means the language is there, but we don't know how to really, make it work.
Mm-hmm.
So if you push me, I could agree with you that maybe we should leave gravity a little bit aside, okay? But there is no other language which describes gravity. So it's not that quantum field theory doesn't work for gravity, and there is another description which does work. No, so far quantum gravity defies, so does not like any description fully, even though there is little doubt that something like quantum field theory will have to work, but we have not found exactly what. But in all the other cases, yes. In all the other cases, the agreement is spectacular. I mean, it's not as spectacular as in the case of the G-2. So that's the G-2 example that I described. This is not at this level of precision, but the precision is very, very good. Very, very good. Like, you know, could be like 3 or 4, depending on the object. In all cases, and apart from gravity. But as I'm saying, I mean, gravity, I think that at some point, we are going to be able to describe it as a quantum field theory. Or at least that's the hope. Okay, any other question?
Yeah, I would like to ask a question.
Mm-hmm.
Does the Higgs boson need to interact with its own field in order to have mass?
No, it does interact with itself. So there are, in the interactions of the Higgs, there are, you know, self-interactions. There are the so-called self-interactions, but those are not related to the mass. The Higgs field has a mass, even without interacting with anyone.
Okay.
As the electron, the electron also has a mass, even if it is free. Even if we had an electron in the middle of the universe, okay, completely away from any electric or magnetic field or any other field, it would still have a mass.
But that's because it's interacting with the Higgs field, no?
Yes, that's the way we understand it. Yes, that's the way we currently understand it. That it is a consequence of interacting with a field that is related to the Higgs field. Yes. But yes, so that's the way we understand it. Yeah. So I was trying to give you a simplified version. Yes. Currently, we understand the masses of particles as the interaction with the Higgs field. But that's because we assume that the Higgs field, you know, fills all the space always. Okay. Even though we don't see it, if you wish. Is one way of understanding the mass of particles.
So where the Higgs mass comes from?
The Higgs mass, in a way, if you want to say that all the masses come from the interaction with the Higgs, then the Higgs mass also comes from the potential that the Higgs has with itself. Okay, so the Higgs, in this new version, the Higgs is responsible for all the masses, yes.
Okay. Thank you.
But all this you guys are going to see if you take in detail, right? I mean, in all the explanations that I'm giving right now, I cannot do full justice to you know, I cannot give you all the details. And you guys are going to find more detailed explanations if you guys in the next semester take high energy physics or advanced quantum mechanics. And there you're going to see, you know, what all these words mean, right? All these words mean. Okay, any other question or comment? Okay, so if not, we're going to leave it at this point. The next day, we're going to describe Nether's theorem for field theory. And so this is going to be, you know, a very long theorem that we'll have to prove. And as you will see, is a very interesting and powerful theorem, okay? But for today, I think it's enough.